Welcome to this session of Shadow the Scientist. My name is Jamika Marshall, and I'm very pleased to serve as the Shadow the Scientist coordinator. Shadow the Scientist is housed under the Creating Equity in STEAM umbrella of programs, which is offered by a team at the University of California, Santa Cruz. In this session, we have the privilege of shadowing a stellar team of astronomers. Zhuo Chen, a postdoctoral researcher from the University of Washington, and Raja GuhaThakurta, a distinguished professor of astronomy and astrophysics at the University of California, Santa Cruz, who is also the founder of Shadow the Scientist. They will be our guides on this session. Now, they and their colleagues plan to use the Keck I 10-meter telescope and the OSIRIS instrument, and we'll learn what that acronym means, the OSIRIS instrument to study the kinematics and chemical composition of the stars that make up the nuclear star cluster of the Triangulum galaxy, M33. Now, let's head over to Raja to get us started. Welcome, Raja.
Thanks, Jamika. I'm going to share my screen, yeah, there we go. We have four screens worth of data to show you. So for starters, I'm going to put in the chat what OSIRIS stands for. I'm just typing into the chat. Bear with me. That's what OSIRIS stands for. It's a mouthful. I'm looking for a web page. You can see me do this. There we go.
While Raja is getting ready, I'd like to welcome everyone to this session again of Shadow the Scientist. And I want to let you know that your questions and comments are welcome in the chat at any time. Also, if you'd like to ask your question out loud, just raise your virtual hand and I can unmute you to ask your question.
I'm going to put this link in the chat. This is the a page that tells you about OSIRIS. I've just put the link in the chat.
Now, observations are already underway, and Raja is getting ready to share with us some of the screens that are being used during the observations at the Keck Observatory. Now, Raja, I believe you are actually here on the Big Island, correct?
I'm on the Big Island, exactly. And we're observing a telluric standard now, Zhuo? Is that right? Okay. We're observing a bright star that's very high temperature bright star, so that it doesn't have much by way of its own spectral features. And we take that and we instead of taking an image, we slice it up into a bunch of spectra. That's what you're seeing in this blue screen on the right. The reason so what happens is we're working in the infrared today. We are, where do can I find We were working in what is called the K band. This is the K band is at 2.2 microns. So we're working in the infrared spectra.
Magnitude's translating. Okay, no worries. Okay, I can do it.
Folks, we're just getting set up to go to our first science target, which is the star cluster at the center of M33. So please bear with me 1 minute, but what you're seeing over here are these spectra of this bright star. You can see that the image of a star doesn't land on a single pixel. The light of a star doesn't land on a single pixel. It's spread out over multiple pixels. And then we are taking that light and dispersing that into a spectrum. That's what you're seeing in this. But Matt, I'm not seeing it in the guider. Oh, yeah. Okay. How do I do that? Oh, there we go.
I just gotta reset a fetch for the right magnitude.
Yeah, okay.
Huge.
That was Z scale. I'll set it back to mean. Does that mess you up, Matt, if I set it to Z scale like this?
There's no offset?
About an arc minute, I think.
Okay.
So folks, we're looking down I'm going to stop my screen share for a moment. What we're doing here is we're looking down right down the center of a galaxy called the Andromeda Galaxy. Sorry, the Triangulum Galaxy. We're looking at the nuclear star cluster. Nuclear meaning at the very center of. I'm putting this in the chat. That's our main science target for today. And Rohit, unfortunately, we're not getting any Wolf-Rayet stars targets in M33 tonight, because it took us too long to get the adaptive optics going. By the time we got it going, we had to go straight to the science target, the primary science target.
All right, we need.
Thanks, Jamaica.
Yeah, go ahead.
Yeah.
Please take a moment to go around. We can go around the Zoom room, have each person say a little bit about how they found out about shadow and what research they're already doing. You know, Rohit, Stephen, Stefan, you're welcome to do the same. Kavya, same for everyone. You know, tell us a little bit about what you're studying, if you're doing research, what research you're doing, and what else? Let's go in turn. Let's start with Rohit. Rohit, take it away. Rohit,
Roger,
is
do
that
you
okay?
want me to unmute everyone,
Yeah,
or
let's
do
do
you
that. It's
want
a
them to
small
put
group.
the
Yeah,
information in the chat?
yeah. No, let's unmute. It's a small group, so
Okay. Rohit
thank
is
you.
already co-host. So yeah, go ahead, Rohit.
Hello everyone, I'm Rohit Raj and I'm a senior fourth year undergrad student at GuhaThakurta College, and I have been doing research with Professor Raja from over 2 years. I study right now, one of my project is on unusual stars in Triangulum galaxy, which they are studying tonight, and also Andromeda and M32. So we look at some of the exotic stars and how they behave, what will be their future, and what they will end up into.
That's right. Let's go to Stephen next. Hey,
Hello,
Stephen, your poster
everyone.
has been. Hey, Stephen, your poster has been moved. It hasn't been removed.
Yes, Paulina told me and told me about everything, and I was not offended at all. I was just happy that it's still up, but
Yeah, I had no control over the move. I came back to find it moved. Right, go ahead. Sorry.
so hi everyone, I'm Steven. I'm a senior undergrad at UC Merced. I started doing research with Raja over the summer where I looked at 6 star clusters in the Andromeda galaxy using Hubble Space Telescope and Keck II telescope in Hawaii. Keck II is a ground-based telescope which could get interference from Earth's atmosphere. So we looked at these star clusters using adaptive optics. And I compared this to Hubble, which did not have interference from Earth's atmosphere, and I saw which telescope gave us sharper images. I then used these images to search for variable stars, and I also created 3D models from them.
Stephen, what we are looking at tonight is a single star cluster, not in Andromeda, but in Triangulum, as you heard, at the very center. So we're not looking at 6, just one. And tonight and tomorrow night, we'll image sort of adjacent patches. The patch we cover with adaptive optics is quite small. It's 3 by 6 arc seconds. So it's a long rectangle. And tomorrow we'll cover an adjacent 3 by 6. So in the end, we'll come away with 6 by 6, which is just big enough to see the center of the cluster and the outskirts. This is with adaptive optics also, but with laser guide star adaptive optics. We're using natural guide stars as well as laser guide stars to do AO tonight and tomorrow night. Now, the other thing is we're taking images in the infrared in the K band. Remember, we had images in the H and K bands. This time it will be in the K band only. But we're taking not images, but not a single image in the K band, but images at every wavelength, slightly different wavelengths in the K band. You can think of it as a data cube. You have a single image in one filter at one wavelength. Think of it as a very narrow band filter image. And then if you have another image where the band is slightly shifted, so the next set of wavelengths, and slightly shifted again, you have a series of images like that, thousands like that, so that what you form is a data cube where you have n pixels by n pixels in the sky, and then a third number of pixels in the spectral direction. So these are 3-dimensional data cubes. You have RA, DEC, and wavelength as the 3 axes. So that's one of the things we're doing tonight. Now, it would be very cool to make 3D images in the K band of this cluster. What we would do is collapse all the spectral information. So we would get a combined K band image. We would basically take the data cube and collapse it in the spectral direction. So you get a K band image at that point with adaptive optics. And so we don't have H band images, but we actually have JWST JWST images of this object. So it'd be very cool to do these comparisons. Anyway, we should go on with the introduction. Thanks for the intro. Javier, you're next.
Uh-oh. Okay. Hi, my name's Kavya. I also study at Juniata College. I don't know, I was doing my homework and Rohit told me to join today to see a Shadow the Scientist program like in real because I'm meeting with Jamaica tomorrow about this. So I was like, might as well kind of experience it on my own. My research field is very different than you guys. I currently work on bioinformatics stuff, and we look at like human gut microbiome and how certain foods that we experiment on, like how does that affect our gut and kind of, yeah. That. I think Roger, you're mute.
Are
if you're
you and
something.
Jamaica talking about the possibility of hosting a
Yeah, I
research
think we're
session
meeting
on that?
tomorrow about this. Yeah.
Excellent. Let's go to Ravi next. Ravi Raj. While we're waiting for Ravi, Stefan, you want to introduce yourself? Go ahead, and you can unmute.
Sorry, I'm muted so we don't get echoes, but
I can
oh
turn
wait.
mine off. Go ahead.
Hi, I'm Stefan Kimura. I work usually with the Salvation team, but Raja invited me to come help him and Joe with their observing at Keck tonight. So I'm here kind of shadowing and helping out if I'm needed. But yeah, nice to meet everybody.
Good to see you, Stefan.
All right, Richard is next, and then Rob. Richard, if you want to take a moment to introduce yourself, please go ahead. All right, Rob, you're on.
Okay, hi. I'm Rob Johnson, zooming from Los Angeles. I'm a mathematician, amateur astrophotographer, and been to quite a number of the Shadow of the Scientists so far.
It's always fantastic to have you, Rob. Thank you.
Thanks.
As well as you too, Richard. Thank you.
Thank you. Can you hear me?
Yes, Richard, we can hear you now.
Okay.
We can hear you.
Hi.
Did you want to say
I'm,
anything by way? Yeah, go ahead.
I'm just
Sorry.
a hobbyist, interested in science and astrology and astronomy. I'm just about to turn 70 years old, so it's been a while since I've been in college. But I always enjoy, these Zoom meetings. So
Fantastic, Richard. That's amazing. I'm so glad that you are with us for this session. And I'd like to welcome everyone, Rohit, Stephen, Kavya, Stefan, Ravi, Richard, and Rob. Wonderful. And I guess I introduced myself earlier, but again, if you're just joining, my name is Jamaica Marshall, and I am the coordinator for Shadow the Scientist. My research right now is in doing support observations for for NASA's Lucy mission to study the Trojan asteroids of Jupiter. Currently doing observations of 617 Patroclus, which is a binary asteroid. We're helping to prepare for their 2033 flyby, which is very exciting.
Wonderful, Jamaica. That's fantastic. All right, I'm going to share my screen one more time. So I was changing the contrast on this guider image here. This is the star cluster at the very center. And you can see these patches, these dark patches along the left. This is because of interstellar dust in the galaxy. What looks like a single dot here is actually a collection of stars, and it's only with higher resolution that we can, you can see the individual stars, and in this case, take spectra of individual stars. That's what our goal is tonight, is to get spectra of all the stars, not all, the brighter stars that make up this cluster. Let me show you some of the other. So we've placed the star cluster at the edge of this rectangular field of view. And we are doing this sort of what's called a 2-point dither pattern. We are occasionally putting the star cluster here, occasionally putting the star cluster down here. And we've taken a difference between those two. So you're getting a positive and a negative version of the star cluster. You take an image A and an image B, and you take the difference between A and B, A minus B. The reason we do that is to remove sort of instrumental and atmospheric artifacts. But you can see it's along the left edge here, and tomorrow we'll image the adjacent field so that we'll get in the end, we'll get sort of a square region imaged. Is the image we're looking at here, Zhuo, is this the star cluster? Is this one of our telluric standards? This is the cluster. It's a tip-tail star. I see. It's not the cluster itself, but this close. Okay. And are we doing a BXY5 pattern or a up-down?
So I planning to do box 4 or 5.
4 or 5. Okay. But for the tip-tail star, this was just a 2-point up and down.
To check where it is.
I see. And how come it's not centered in our field of view? It's off to the left. Is that deliberate? Okay, now it's centered. Yeah, now it's centered. Okay. So this is a tip-tilt star we're looking at, folks, not the star cluster itself. It's a single star. And it's called a tip-tilt star. It's one of the natural guide stars that's used for adaptive optics correction, in addition to the laser. One of the really cool things that I just took a picture of this on my phone. Let me see if I can share it with all of you. I'm gonna see if I can share this with all of you.
Yeah, whenever you're ready. Yeah. Once you know what the outfit, I'm gonna go get up some food. I still haven't eaten dinner. I realize I'm like. No, that's on me. I forgot.
So those are in that slot. Okay.
I'm going to see if I can share my screen with you.
Yeah. Can you repeat the?
So while you're doing that, Raja, we got a question in the chat from
Okay.
Ravi about what is that bell that we hear in the background? And that's one of the notification sounds, right? When an exposure is complete?
That's correct. That is correct. I'm not exactly sure of the particular bell, but I believe it has to do with the end of exposures. I'm going to see, I'm still trying to share this image. I tried to send it as a chat to myself, but that didn't go through.
And I put it in windscreen mode to help with the wind.
Roger, you
There's a
could
little-
email
there's a little
me
freebie
the
at the top.
image and then I
Getting
can
like
drop the link to
24
it from
miles
my
an hour,
drive here in
25 miles
the
an hour
chat.
sustained. So-
Sure. I think I'm going to do that right now.
Okay, sounds good.
Do you, should I email or text it to you? Does it matter?
Yes, email it to me, please.
I will do.
And there's no issue for your program. Okay, so we don't have, for this new position, we don't have to take like short of COVID. Cool.
I've just sent it to you, Jamika. What is cool is what I've just sent you is an image that I just took with my phone in the Keck I remote ops room, where you can see the laser shining out of our telescope.
Okay, I'm in my email now. I'm just waiting for your message to pop up.
Sure, no problem.
Oh, so they start from 002, right? Yeah. Oh, okay. So then one.
So this particular object we looked at is what's called the tip tilt star. And now we're gonna, I think we're observing the star cluster next. Fighting terrible allergies.
Oh, I thought you sounded a bit stuffy. I'm sorry to hear that. Okay, I just got your email and I will grab that image and share it with everyone.
And you're putting that in the chat?
Yes, I'll put a link to it in the chat. I'm just gonna add it to my drive real quick so I can have a link to share.
So we are observing from a town called Waimea, Keck headquarters here. I'm putting this in the chat, Kavya.
Got it.
The Raj is in the northern part of the Big Island. So looking out from the control room and from Keck headquarters is pretty amazing because you can look right at the Keck telescopes, which is pretty stunning. I'm in Hilo, also on the Big Island, I'm on the east side, so from my perspective,
well,
I
linked
see
to
the eastern
thither,
ridge of the
depending
telescopes
on how we
near
want
the
to use
summit in
it.
Mauna Kea.
So for example, this time we select the dither in box 5 seconds to move a bit, and the selected line was the step between each dither. So for example, here is the X1 offsets are 0.05 offset. So that's the box.
So one of the things, I guess, Sherry had to, or one of the things we had to prepare for, right? There are times when the laser has to be shut because of interference with satellites and planes, or satellites only? I think only satellites, right? We'll ask Sherry when she comes back. But so that's what they were saying is right now there's no shutdown for the next, for an hour or something, like 4,000 seconds, right? They said so it's over an hour. But this is something you have to be careful about when you're using a laser. These are powerful lasers, so so we have to let people know beforehand which direction of the sky we're going to be pointing the laser at, and they tell us when to shut it down.
So I dropped your image that you sent in the chat. Hopefully everyone can open it.
Let me see if I can access it, Jamaica. I'm going to try.
And I actually have a live view of the laser right now. I'm going to share that.
I can access your image. That's great.
Excellent. Okay, so I have a live view from a different telescope, from the Subaru telescope, as operated by the National Astronomical Observatory of Japan. We had 2 sessions with them last week, including our first Japanese session. And so this image, this is live from Mauna Kea, from the Asahi telescope, Asahi camera from Subaru.
Jamaica, should I stop my screen share so you can share your screen, or how would you share it? Oh, there we go. Okay, you've got it.
Okay, so now you can clearly can see live this view. Is a stunning view of the laser in action.
That's Keck I, right, that we're looking at.
So I'll drop a link to this. This is a live feed. It is wonderful to watch. There's always so beautiful images coming through on this camera, meteor showers, and just beautiful night sky from the summit region of Mauna Kea here with the Subaru telescope camera. So I'll stop my share now. I just wanted to add that to that fantastic image that Roger was sharing with us.
And Jamaica, if we could go back for a second to your screen share, just for
sure.
a second. Is that K2 that you can see to the lower left of Keck I?
Right here,
That's Keck,
should be.
Yeah, that's Keck II. I think I can just see the dome.
Yes, right there. I don't know if you can see my
I can see your
cursor.
cursor. I can
Okay,
see your
yeah,
cursor.
right there.
That's the
And
Keck
if
II
you were
dome.
to keep going over to the right, so to the right of Keck I is the Subaru telescope, which is where the camera is situated that we're looking through right now.
I see. I can see at least 3 other telescopes in this view.
Yes.
Oh,
It's like Canada-France Wide Telescope, maybe right here.
that's what I'm guessing
Gemini.
also, yeah. Gemini.
Yeah, Gemini right here. And that looks like the dome of the NASA Infrared Telescope facility. Right here.
And
I could be wrong about
this, and this star cluster we're looking at has been imaged before by Gemini, also using an IFU, this kind of thing that makes a 3D data cube. It's called an IFU, and this is the generic name for this kind of 3D spectroscopy, where you take a spectrum of every pixel on the sky. Gemini has an instrument, an IFU instrument, that's part of GMOS, the Gemini multi-object spectrograph. So this was imaged with that. But we are redoing this with Keck because we think we can get to fainter stars and more stars for which we can measure chemical composition and velocity. That's the goal of this. It's the goal of this tonight and tomorrow night. So, okay, I'm going to go back to screen sharing. Now, Zhuo, on the guider, we're still seeing the tip tilt star, right? We're not seeing the star cluster.
Well, this is the tip-tailed star, and then we have.
Oh.
Will take 15 minutes.
15 minutes, right? So if I go to the guider, I should see it. This is the guider image, right? So this is looking at the right thing here. So the tip tilt star must be very close to the center. And am I pointing to the central cluster here? You can see my cursor, right? Yeah, okay, good, okay. It's amazing, this sort of region of star formation in the upper right. Is this the nuclear star cluster? Let me change the stretch. Is this the nuclear star cluster right there? Must be, right? Yeah, okay. It looks so bright compared to everything else. I love this view though. Sorry about that. I love the Z-scale view. You can really see the dust lanes on the left and the dust lane here.
We stopped guiding. We stopped the guider exposure.
Okay.
Guider exposure.
No problem. No problem. Okay. The guide. This is the magic guider image, Sherry.
It is.
Okay. It's not updating at all, or it's updating infrequently.
It's not updating now because we don't.
You don't use it.
Expose it.
Gotcha. Gotcha.
We only do it when we're requiring it.
Gotcha. Okay. Sherry, can I send you a Zoom link for our shadow session? I can send it to Matt. What's the easiest way to send it? Can I send it as a email to your email address and Matt's email address? What I've got is a Zoom link that's specific to me. So when you log in, it will have my name on it. So all you'll have to do is just change your name to your own. Otherwise, you'll have to go through a whole registration process.
Okay, can you put that in an email?
Yeah, I'll put that in the email. Yeah, as soon as you log in on Zoom, you'll just go in and change your name. Otherwise, there'll be 3 versions of me on the Zoom call. At one point, we had done this from Gemini. Okay, I will send this to you. Give me a second. I'm going to stop my screen share, folks, for just a second, and so I can share this to. So Sherry is our support astronomer, and Matt is our observing assistant. I don't have Matt's email. Sherry, please share it with him once I send you the email. Thank you. Oh, you did. Okay, okay. I'll just send it to that one then. And yeah, that answers our question. The laser closure is for satellites, not planes, right? that right, Cherry? The laser closure, is that for satellites or for planes or both? Satellites, okay.
We have a T-band sensor that senses the planes, like if they're coming towards the observatory.
I see.
like, You can, like, it's something that usually they only have at like, what's it called? Like a control tower at an airport, right?
I see.
But we have one here at the observatory that can detect planes and it will automatically shudder the laser if there's gonna be one that's gonna be in danger.
I see. One more second and I'll send you the link. Sure, I'm sending it to you too.
Laptop?
You can also just come over. Yeah, you can, and I can just take off my headset and we can. All right, Sherry and Matt have sent it to you. Stephanie, well, if you wanted to, but you're also already connected, so whatever works. Turn off my virtual background. And you are on, and here we are. I'm going to share my, once you introduce yourself, then I go back to sharing my screen. I have the VNC running, so if you wanted to speak, you're welcome to.
Sure. Hello, everyone. My name is Zhuo Chen. I am running the observing session tonight. So we're planning to do the spectra of the stars in the nuclear star cluster of M33 in the very center using the adaptive optics. So in this really crowded, bright region, only the AO system can help us resolve the stars, and then the IFU can help us get the spectra at a time, like for the stars in the field of view. So we have 2 nights. So the plan is to do one field tonight and the other fields side by side tomorrow night to cover the entire central region. Yep. Just let me know if you have any questions.
And sure, what is the field of view, our rectangle? Is it 1/2 or something like that?
Yeah, so this is so in total, we hope to cover 3.2 by 3.2.
3.2 by 3.2. So
Yeah.
the rectangle is 1.6 by 3.2 then?
Yes.
Okay. Sherry, did you want to take a minute to introduce yourself, please?
Hi,
Go ahead.
I'm Mary. I'm staff astronomer at Keck, and tonight, I'm working with Raja and Joel on their science program. And now we're happily integrating on their science field. And I believe, Joel, you just got your first reduced cube. Looks like it.
Wow. Wow. All right.
Yeah.
We have to show
And
that.
so, yeah, Raja, while you share your screen, let
I'll
me.
share my screen then. Okay.
Yeah.
And
And I'm gonna do a plot here to show you a quick spectrum here of the core.
Okay.
Yeah. So if
I'll
you
wait
want,
to share then. Why don't you share first, Sherry, and then I will do this.
Oh, you want me to share my screen now?
Oh, you wanted to show a spectrum, you said?
Yeah, it's already you know in the OSIRIS VNC. So if you share
Oh,
your
it's in
screen,
the OSIRIS VNC. Okay.
yeah,
Okay. Okay. So when I share my screen, they'll see it.
yes, it's in
Okay,
control
okay.
one.
Okay. All right. Let me do that then.
Hang on.
Of this,
Yeah.
when it's north, like where is north and east?
It's a good question.
Yeah.
Is there a
So
couple of these?
so I'm drawing a box around this star cluster, and this is its raw spectrum. So
Is
part
that
of this,
titanium oxide we're seeing?
what was that?
Is that titanium oxide we're seeing? Those band heads?
It could be. So this is roughly wavelength calibrated.
Yeah, I see that. 2.2, 2.29, 2.3.
Yeah. So what I do is in plot, I do depth plot. And then you can go ahead, take over to draw around anything else want to see.
I see.
Okay.
Yeah, go ahead.
Wow, that's very cool.
Yeah, and of course this contains some of the telluric spectra, the OH lines from our atmosphere. That's why earlier we took telluric exposure to essentially look at the atmosphere itself.
Oh, oops, sorry.
And then we can divide that out.
It hasn't been telluric divided yet then.
No, but this is wavelength calibrated. And you can see.
Sorry. Wow.
Yeah.
So we are looking right now, the spectrum we're looking at on the screen is pretty much of the entire star cluster.
Yeah. And you can definitely
Sorry.
go look
Check
at smaller
our-
stuff here. Yes.
Are we seeing the north roughly on top and east roughly on the left? Because it looks like the opposite to my design. So what I don't know what's the view of this.
Hang on.
Able to see that on the
There.
Uh
Did you see it in the?
So did we want it closer to the
Yeah.
edge?
So wow, this is position is a little tricky to me. So let's see. Well, let me check.
Well, I would say after this, the entire box 5 is done.
Oh,
Since your ditter is very small, right? So we
yes.
can look at the rough center of your cluster, and before we start the next set, you can move it to anywhere you want in the field of view, then start the next set.
Is this the result of one box 5 dither or one of the 5?
One of the 5.
One of the 5. I see. I see.
And we're using a 900 so this is a 900-second exposure. And earlier we took 900-second darks. So we're using the darks as the pseudo background so we can look at a
Gotcha.
quick reduced cube. Yeah.
I see. So this is a single 15-minute exposure and we're doing a pattern of 5 of these.
Yeah.
Gotcha.
And it's because there's no satellite closure in this box
Yeah.
5, I believe. So it's going to be uninterrupted for a while, which is very good. It's very good.
Yeah, that's great.
Very efficient.
But what is amazing to me is how sharp the individual stellar images are, because the dimensions of this box are 1.6 arc seconds by 3.2 arc seconds. I mean, I'm in a ground-based image, a star in good seeing, if we had 0.5 arc second seeing,
Yeah.
star would be a circle whose diameter is 1/3 of the width of this rectangle.
Yes.
Right? Isn't that right? I mean, am I doing my math correctly? 1.6, take 1/3 of that, you get about 0.6.
Yeah.
You get 0.5, actually, 0.55.
Yeah.
That's amazing. That is amazing.
And today our AO corrected image quality measured from a bright engineering star. It was 46 milliarc second.
46 milliarc seconds. That's
It's sharper than your pixel scale here. Your because you're using 50 milliarc seconds scale.
Yeah, 50 milliarc seconds is a pixel scale.
Yeah.
So basically, it's about a 1 pixel full width half maximum.
Yeah, basically. Yeah.
Wow, that's incredible.
Amazing. Thank you. We like to hear that.
No, it's really amazing. I sent my wife an image of the photograph that I said. She asked me, "Is this the first time you're using laser guide star AO, or do you do this all the time?" I said, "This is my first time using laser guide star AO."
Well, although you could also see that the overhead can be high when we're setting up. So there's a trade-off.
No, it's a trade-off. It's absolutely. And one of the first questions she asked me was, "Do you have to be careful so planes don't fly along the path and get distracted?" I said, "Yes, absolutely, we do." Because she works in space. She works for NASA, and so she understands these.
Yeah, cool. Yeah, that's why we, like Matt mentioned, we have this transponder, the transponder signal detection system. So when the airplane gets too close, we turn off the laser. Now, in the past, before we have this automated system, we sent people outside to stare at the skies. They're called laser spotter. They're called spotters to look for airplanes. That was a real job.
Yeah. Yeah, I know Richard asked what we're looking at, and Jamaica, you did an excellent job of answering that. If there are questions about what we're looking at here and why, happy to say more. I mean, Zhuo is an expert on this. Is there, I'm going to see if I can find the exposure counter here.
Oh, Joel, can you mute the microphone and next to your computer? That's the one Zoom. Yeah, can you mute that one?
Thanks. Yeah, if you guys have any questions on the operator, yeah, this is really good conditions tonight. The AO's doing a really good job. Yeah.
Matt, please introduce yourself. We haven't heard.
Hi guys, I'm Matt. I'm the telescope operator. So I drive the telescope for the scientists, get them set up on target, and operate the AO, which looks like that. See it? Anyway, yeah, I drive the telescope for the scientists at night and keep it safe whenever they want to open up in case, and it's raining outside. Yeah. If you guys have any questions, I'm here for you.
Matt, you're the only one among us who's actually at the telescope?
Yeah, I'm up at 14,000 feet right now, which is probably why I look haggard, tired, but yeah. It's we're operating from the summit at about 14,000 feet above sea level. So there's like 60% of the atmosphere up here, which is why it's such a pristine observing spot, because you're above all the moisture and you're above all the atmosphere. So, but it takes a toll on you. So like every breath you take up here, you have to take, or every breath you would take at sea level, you have to take like 2 breaths up here just to like make up for that pretty much. So you walk or you talk.
This is like a line from a song by the Police.
Yeah, right. But I love it. Yeah, wouldn't have it any other way.
No, thank you, both Sherry and Matt. Without you, none of us would be able to get the scientific results we're trying to get. So,
no, seriously, it's our passion and pleasure. Yeah.
So I'm gonna jump back to the work Zoom, if that's okay with everybody.
Sure.
Well, thank you for joining us, everybody. It's nice to have you.
Thank you.
Yeah, thanks so much, everyone. I'll hang out for like 5 more minutes in case anybody's got questions for the operator side of stuff. But yeah.
Oh, before I leave, I guess I could do a quick summary of my job as a staff astronomer. Actually, it's kind of like an ER doctor. So if anything happens at night with observation, I'm the first point of contact. either Matt, our operator, or our observers like Raja will call me. It's whether it's software, hardware, or where is coffee station, or observers lost their code to enter their room. That actually happens more often than you think. Anyway, but so they all call me, right, for troubleshooting, and I decide if I can troubleshoot myself, I'll do it, or I decide it's time to wake up other people, engineers, to help, for example. But the good thing is no one's dying, no matter how bad things are or how challenging it is. No one's dying. Oof. And the sun will rise. So at some point the night ends.
Always.
Oh, but most of the time, one of these nights, right? Like tonight, yeah, we're very happy. So conditions are good and everything is behaving. So that's great. All right. Well, if you have more questions for me, you can tell Raja and Raja can relay it to me later. And now let me go stare at the work Zoom just to be sure.
Thank you, Sherry.
Yeah.
Thank you, Sherry. Matt, I believe you did share a bit about your role. Now, are you the only one there in the observatory near the summit, or is there someone else with you?
We have a 2-body rule. So, worst case scenario, I pass out, somebody can come, rescue me. But yeah, Arena is over on K2. But sometimes we'll have like one person here and one person operating remote down where Raja is. And in that case, we'll have one of our night attendants up here as like a warm body to help, for safety and in case we need an extra set of hands, hands on at the summit to actually like flip a switch or something. But we're moving away from all that as we go towards Ingudao. Yeah.
How many nights in a row do you do this, Matt? How long is a typical shift?
5 nights on is 6 nights off is my typical schedule, and we run 14-hour nights. So the way that it works is we tend to get like 2 weeks of like 40-hour work done in like 1 week usually. So that's why it's like 1 week on, 1 week off, kind of is like the cadence. Yeah. And then we have like a little bit of office work to kind of like make up the difference and to contribute, our knowledge back from the night to the observatory, right? So yeah. I particularly work with AO, so this kind of stuff is like my bread and butter. I did my master's at Palomar, doing direct images of exoplanets with the P2K system. So this is like my bread and butter. And within the observatory, I kind of act as the link between the operators and the adaptive optics team for communication in both ways, right? So what's going on that we can do better from the operations side, right? Up to the AO, and then from the AO back down, like what's going on the engineering side so that we can understand better, and operate the telescope better and get you guys the best optical quality that we can, right? Yeah. All right, I'm gonna jump to the work Zoom too, but yeah, if you have any questions, feel free to, relay them. Yeah.
Thank you.
Thank you,
guys.
Matt.
Pleasure. Yeah.
I'm not at all used to the GUI. OSIRIS GUI.
Is this your first time using OSIRIS?
I think it is.
Sherry, I just sent you a quick screenshot of my finding chart. So currently, according to my offsets stuff, I think I chose the center of the box.
Yeah.
On the left as our new position. So
Yeah.
I thought that was the correct. Yeah.
Wait, so it looks like
Yeah, so it looks like we're kind of targeting
east of north. Wait, then your actual PA should be 12 instead of 348.
But PA is okay. Because we want to be tilted. We want the compass rose to. I think
Yeah,
348
right?
is correct.
East of north, I'm looking at your compass rose and hers.
They match. They match.
No, I
That's
think the, well. I thought the rotation is okay. I think the field is moving towards to relatively north and northwest than I expected. Does that make sense?
Yeah. So do you want to check your offset again from your little star to the target?
So yeah, I can see.
And I just want to say this is not a bad thing that we've got some images with this thing centered, because when we stitch everything together, it'll be helpful to have some of these images where the star cluster is not on the edge.
Sure. So I just want to, yeah, so question, for example, when I specify the offset here, the new position should be the center of the field, like a box, right?
Yes.
Yeah, I think that's the one I said.
So folks, what we're trying to do is get
So what
this.
we can do later is to move your star cluster from here to like here.
Okay.
Not even that far up, maybe more closer to the.
Here.
Yep, sorry about that. Yeah. Little north of it? Okay. Okay.
Yeah,
Yeah,
because
so
this, if
that's
this is the
problem
finding chart,
Uh-huh.
so this is the what I originally planned.
Got you, got
And then
you.
this is, I think,
What we're doing
they
now.
look like now. Yeah, we can.
Yeah, I
Yeah.
see what you mean.
So once this is done,
Okay,
we
sure.
will return. Yeah, we should wait for this offset is done.
Sure.
I think it's better. Yeah. Then once it's all done, you will return to 0, 0.
Okay.
And then from there, before you start another set, let's move star cluster from this pixel to say up here.
Okay. Sure.
Then you start the set. Yeah, and that should be.
And after this box 5, do you recommend we go to sky first, or we can just change the position and run it another set?
You know, because the offset is not always like super accurate, right? As we learned. So I think while we are on target, I think it's good to just send it offset, stay on target, and keep doing. Unless, let's check the closure later. I mean, later the closure is all pretty short. Oh, there's one that's at 5 minutes.
There's a 5-minute one, yeah.
Yeah. Okay. And we still have 3 more to go. We have 3 more to go.
Where are you seeing this, Sherry? Which window?
Oh, that's in AO.
Oh, okay. No, I'm seeing it. 3 of 5, it says. Dither position. It's on position 3 of 5.
Yeah, you can see OSIRIS somewhere. It's also highlighting the center position. Here.
Got it.
Only this one.
So it's in the upper right one now. Or upper left, I guess. Upper left, because those are.
So,
So folks, if you imagine the dots.
the laser closure is gonna happen in your very last exposure.
Okay.
Or maybe actually, I think your very last exposure is gonna happen right when laser closure is starting.
You mean this
Perfect.
set?
Yeah.
The 5th one of this set.
So in such case, there's a 5-minute exposure, then we may as well go take a sky.
Okay.
For 50 minutes. And when we come back, what we can do is you send your offset, but before we start a 900-second exposure, we can take a really short one to see where the core is if you start clustering.
Sounds
Because
good.
it's so a much shorter exposure, we can just see the core. We don't need to capture the neighboring stars.
Okay.
That sounds good.
Yeah. Back to galactic center, tactic.
Yeah.
Right. Sure. A really short, say 60-second exposure, see where it is. Then
So folks on Zoom, what we're doing is what is called a BXY5 pattern. So we are, if you think of the, if you think of a pattern of 5 on a face of a die, there's a dot at the center and then there's 4 dots in the 4 corners. If you think of where we're pointing the telescope, we're forming a pattern like that. We're taking a pattern of 5 images, and this is called a dither pattern, where we're moving the telescope by a small amount. The amount is 0.05 arc seconds. So it's 1/20th of an arc second. And you can see in what I'm highlighting here, we did a 0, point. So it's the central point of the pointing. We did one at minus 0.05, minus 0.05 from that. Sorry, plus 0. So that's like the upper left. But because minus to the a minus in x, plus in y, then we did, now we're doing the plus 0.05 plus 0.05, so that's the upper right. Then we'll do the lower right, and finally we'll do the lower left. So this is the pattern of 5 15-minute exposures we're doing. And the reason for dithering is multiple, but these detectors are not perfect. There could be pixels that are less sensitive than they typically. Not all pixels have exactly the same sensitivity. So you don't want some unfortunate star's light to always fall on the same pixel. This dither pattern ensures that we are spreading the pain, that bad pixels hit different stars on the different exposures, so we can sort of average over that. We, of course, correct for the lower sensitivity of some of the lower sensitivity pixels. We do that, but we still take a hit in signal to noise ratio, and we can spread that pain. To answer your question, Stephen, there are the nuclear star clusters of galaxies, things that people are still trying to understand. They are not that different from globular clusters. That they vary in richness. Not all star clusters are the same. Richness meaning in terms of number of stars that make up the cluster. This is true for nuclear star clusters. They certainly don't all have the same richness, just like globular clusters don't all have the same richness. They are generally old, like globular clusters. They vary in size and in density, but there are some, I believe there are some nuclear star clusters that have young stars in them as well. This one at the center of M33 appears to be an old globular cluster-like star cluster. Sure, this is a great question from one of our students, Stephen. He's asked, how different are nuclear star clusters from globular star clusters in terms of age, size, and density?
Well, so globular clusters are generally a lot older
Than nuclear star clusters?
than nuclear star clusters, I think. Yeah.
But this one is an old cluster, right? This doesn't have young stars.
Well, it depends. So according to our current understanding, it might be just a few gig years old. So
Okay.
not as old as those like
Globular
10
clusters. I see.
years old. And then depending on how massive the host galaxy is, it could be a lot more massive than the globular clusters, or
Gotcha.
depends. So for example, the Milky Way one, the nuclear star cluster is like, well, 2 times 10 to the 7. So
Wow, that's
yeah,
a lot.
that's a lot. Yeah.
I thought 2 times 10 to the 7 was the mass of the black hole. Isn't it 20 million solar masses?
That's I think the black hole is 10 to the 6. Like four.
Oh, Andromeda is 2 times 10 to the 7. You're right.
Oh,
It's 10 to the 6. Yeah. 10 to the 6.
Yeah.
4 times 10 to the 6. I
Yeah.
see.
Depends.
So that's
nuclear
yeah, okay. So if it's 2 times 10 to the 7, That's much more massive than a typical globular cluster. So about 10 times that.
And the globular clusters are mostly like throughout the whole galaxy.
Throughout the galaxy,
Yeah,
right, right. So they're like star clusters. They're superstar clusters in terms of size and mass. The nuclear ones are.
Yeah,
they're
and
big.
also it is the brightest cluster
In
uh,
M33.
in one galaxy. So it's
see.
usually a lot brighter than other clusters.
And this is true for M33 also. This is the brightest star cluster.
Yes, I think so.
Although some of the star forming regions are very bright, right? But those are
Yeah, so I think it's the brightest and most massive cluster.
cluster. I
Yeah.
see. Yeah. The star forming regions are more diffuse, right? They're bigger.
Yeah, and this is densest, most massive star cluster system.
I see. I see. Stephen, I hope you could hear that this is they are sort of extreme star clusters. They're not like the other globulars. Is there an exposure counter in the GUI? Oh, maybe it's this thing that's at 75%. Yeah, that's it. This is the thing that's counting up. Right, Joe, is this the thing that's counting the exposure?
Yes. This specific rate.
Okay, and the 740, 741, that's the number of seconds out of 900, right?
I think so.
It says I time 899.91. That's the total exposure time.
Yeah.
Okay.
Just
Yeah, bar. Yeah, it's going up.
yeah.
I can see that. That's going up one per second. Yeah, I see the percentage as well as I see both. It looks like it's going for 9:49 seconds for some reason. Not exactly. You see that the end of the bar is 9:49 seconds.
I don't know if that includes some.
Might be some of the reads. Yeah.
Yeah.
Because I think it says I time is integration time, and that is 900 seconds.
Yeah.
And it has 32 non-destructive reads, right? So
Yeah, the spec I time.
yeah, okay. Spec I time, and then the actual achieved time is close to that. So it does 32 reads within this during these 15 minutes, so as to not saturate the detector.
So
It does 32 reads during the. Oh, it reads on its ramp up to the full readout. The 32 reads are intermediate reads, because it says that looks like they're 32. Where did I see 32 reads? I saw that somewhere. Oh yeah, it says reads 32. I think that's automatic. I think that is.
Yeah, I specify the coax, just one.
Okay.
And 900.
This is going on here. Joe, you had the. This is very useful. What you have there. Are you able to share that with the group here by any chance? How can I?
Well, I'm not sure. This is some published.
Oh, right.
Yeah, so this is JWST one. We
Oh,
are
okay.
about to.
Gotcha. This is a JWST image?
Yes.
Wow.
So this is the JWST. Like the PI is Eric Roslowski.
Right.
Yeah. And
But
then,
this was imaging, not spectroscopy.
imaging. Yeah. So it was the parallel one. So they were mainly targeting the mirror data, the nearest one, and then the nearest back,
I see.
near cam is the in parallel.
I see. And what were they getting a spectrum of? This is parallel imaging, this one?
So this yeah, it's just the
Parallel images.
yeah.
What was the main primary target? Was that a spectrum?
No, also the image, the mirror image.
Oh, MIRI.
Yeah.
Like mid-infrared.
Yeah.
And what part of M33 were they imaging?
I think, well,
This is a beautiful image. It's really lovely.
this is the near term, the entire field of view.
I see.
This is the mirror one. They're
I see.
targeting the spiral arm stuff.
Oh, it's on the spiral arm. I see.
Yeah, some stuff.
I see. So MIRI and NIRCam are actually adjacent fields. They're not overlap. They don't overlap.
No, yeah,
I see.
no,
So NIRCam was on the center and MIRI was imaging the
the
spiral arm. I
yeah.
see.
So
I see.
we got some new cam data. That's the
So what Zhuo is talking about, guys, is that
Can you let me know when we're kind of in between an exposure? I'd like to take any background for the AO now that the sky's gotten darker.
Oh, sorry, can you repeat? What do you want?
I'd like to take a new background at some point for the AO system. So can you let me know when we're kind of like in between an exposure set?
Yeah, I think this is the
it's the third one, right?
4 out of 5 frame of this set. And I think the very last one may hit the laser closure. So we might be able to do what you need then.
Okay, no worries. Yeah. Whenever we get a chance. Yeah. Thanks.
I think we're about half an hour away, Matt, because we
Yeah.
just started the 4th out of 5.
Gotcha. Okay.
And these offsets are tiny, right? These are 0.05. So it's hard to see.
Oh yeah.
These offsets are very small.
Just a small distance.
But to the folks on Zoom, on the shadow session, just a quick thing, which is some other members of the team that Joe works with, they got some time with James Webb to get mid-infrared images of one of the spiral arms of M33. And one of the things that space telescopes do, Hubble does this, James Webb does this, while one instrument is taking data of a certain kind, another instrument can be turned on at the same time. So that two cameras can be operating, or a camera and a spectrograph can be operating at the same time. So what they did was they took mid-infrared images of the spiral arm and they took near-infrared images of this nuclear star cluster using 2 different instruments on James Webb. And that's what we're using as our reference to orient ourselves and figure out exactly where we are taking OSIRIS data. Go to this other image. So this should be a new image right now, right? This one that we're looking at. This image should be the latest readout, the third dither.
Yes, exactly. That's the 004. You can see the title of the file. That's the file
004. I see. So 2 was the first one. 002 was the first one.
Yeah.
3.
Oh, yeah, from 2, 3, 4.
2, 3, 4. Because
Yeah,
I think
it's
it's during the 4th one, which would be 005. And I think it shows that in this column, it shows that the one that it's working on is 005 over here. Oh, 15 minutes seems like such a long time. How big is the field of view of the magic guider? Oh, we can see that here. It actually says it's about an arc minute at the bottom. Stefan, you were asking, right?
Yeah.
And you can see a bar at the bottom. It's about 60 arc seconds. So it looks like it's something like 90 by 90. I would guess that the bar is about 2/3 of the full field of view. So Rohit, one of the things we're trying to learn here, basically chemodynamics. We're looking to see how things are moving in the star cluster. We're looking to measure the velocities of objects, but we're also looking to measure the chemical composition of stars. So we're looking to measure both things, right, Joe? That's the main goal of these observations. What will our velocity precision be for individual stars, roughly? A few kilometers per second.
That the goal is to get around like a 3 kilometers per second.
Precision? Okay.
Yeah.
And that's comparable probably to the dispersion of the cluster, right? So the cluster should typically star clusters have a few kilometers per second dispersion. So we'll be able to tell if something is a non-member of the cluster just superposed on the face of it. That we should be able to tell.
It depends, because according to the Gemini spectroscopy, they found some internal rotation stuff, and they
Within the
according to-
cluster.
Yeah.
Wow.
And according to, so that's why they identified as like nuclear star cluster stuff, but I don't think they could really separate out members versus non-members. using kinematics.
Okay.
Yeah, so it's a little tricky, I think, according to what they said in the paper, they did not claim.
I see. Well, the spectrum gives us velocity, gives us chemical composition, but also gives us like the spectral type of each star, which is information that is, we have color and brightness information, presumably from JWST. Is JWST in 2 filters or 3?
4.
4 filters.
Yeah,
Wow.
2 short wavelengths, 2 longer wavelengths. But I think the 2 shorter wavelengths are useful.
I see.
But
all in the sort of near infrared region.
yeah, 090 and 200.
090 meaning 900 nanometers? No, no, no. Infrared. Okay, so like far red, beginning of the infrared. So 090. So 090 must be 0.9 microns. 0.9 microns, right, is the shortest wavelength. And then slightly longer from there. So is this very reddened, the star cluster? Not very. Probably not, right? This is quite a face-on galaxy.
Yeah. I think it's just
I should send a picture like this to Jamika. This is such a cool picture over here. Have you seen this?
Real time, those are real time images. Yeah.
Gemini
This looks like a cake.
Direction is the middle picture pointing see south. Is that what? Oh no, blue. So north.
Same north.
That's pointing towards us.
Pointing towards us, towards where we are. Yes. It keeps changing, I think. Because it keeps going around this, I think.
Follow us.
Maybe, I don't know what, yeah, or it may just rotate around. It's such a cool thing. Yeah.
We were on the lit. On the lower. And I figured I asked Stephanie to take over, so I went and get.
Oh, sorry.
They got all our stuff together in case we had to run.
Oh, sorry. Oh. Jimika, I'm sending you another photo that I just took off the Keck cloud camera. Spectacular image. Please share it with the group once I send it. I'm about to send it. I think this is the Keck cloud camera, right? This must be. Jimika, I just sent you a second image. Yeah, Rohit, the overall goal is to get a better understanding of how nuclear star clusters form and, why their properties, why and how their properties correlate with that of the host galaxy. Sure, is that fair? Saying that, the purpose of this observation is to understand nuclear star clusters in general, not just in M33.
Yeah.
Right.
So to estimate the higher metal star versus lower and estimate if the lower metal stars come from the acritic halo component or just part of this another like infall the star cluster or dwarf galaxy itself. So some kind of origins of the nuclear star cluster in general.
See how this exposure is going. It should be close to done with number 4. Exposure 005, which is the 4th in the dither pattern.
Close between these 5 exposures.
No, they won't close the telescope. They'll just shut off the laser.
That's the other issue. I don't know if you heard about.
Oh, wow.
So I guess the machinery is like falling apart, so they're trying to reduce the wear and tear. So
Wow.
you gotta be real careful. Not that it's matter these last few months.
Yeah, no, that's awful. Things are really breaking down.
0.005, is that arc seconds or these offsets for the dither positions? Are these in arc seconds?
Yeah, so
So
0.05, 0.05, yes.
I shared that image that you sent from the Keck Cloud Cam here in the chat, Raja.
Oh, thank you. Yeah, Rohit, the velocity dispersion, if the cluster is in equilibrium, then the velocity dispersion is, of course, related to the mass of the cluster, the overall mass, dynamical mass. So sigma squared multiplied by r, the radius, which is something like a half-light radius. Sigma squared multiplied by r is related to the overall mass, the gravitational mass. But if the cluster is out of equilibrium, then the dispersion isn't necessarily telling us about the gravitational field. So understanding the kinematics of objects gives us more information than images alone. Tells us about the dynamical state. If the cluster, for example, if the cluster is rotating or if the cluster is being tidally disrupted, these are all things you can learn potentially from spatially resolved kinematics of stars. So we've just started our last 15-minute exposure of this set, 006. Sure, what is the A011 in the name? I see S241120, that's the date. What is the A011 before?
That's the sets number. So every time we set the set to Q and then start next data set, it starts a new
Sequence.
set name.
I
So,
see.
For example, from my log file in our afternoon calibration, we took some darks, that's like set 1. And then
Okay.
we took the telluric star, that's set 2, 3, 4.
I see. So no, this is set 11 then.
Yes.
This is set 11. And then why did the numbering start at 2? What was the first one? That was just a check? Because we are at number 6, even though it's the 5th exposure. What was A011001?
It does that. It always start from 2.
It starts from 2. Okay, okay.
Yeah.
No problem. Okay, that answers my question. You know, you have 0 index counting, you have 1 index counting, you have 2 index counting, I guess.
Apparently, yeah.
I think that's what.
Yeah, I think so, because they'll have a 5-minute laser clip.
Okay.
Is the laser closure going to impact this exposure, or will it happen after this exposure?
We are 450 seconds away from that.
Oh, wow. Okay. We have almost 900 to go, 800 to go for this one. Actually,
Yeah. Under the laser, so your last part of the exposure would be
No laser, yeah.
no laser.
see.
So that one, the image quality wouldn't be as good.
Okay. But for most of the exposure, the laser will be operating. So I guess most of the integration will be fully AO corrected, but just the last part won't be.
Yeah.
So
Yeah, last about 350 seconds will be no way out.
As no AO. So I guess it'll affect things like the Strel.
Well, then actually, once in such case, the laser closure will be done when your very last exposure is finished.
Okay. And then we can.
Then we should just stay on target.
Sure.
Consent.
Yeah. And we can, I can move, as you said, move the stuff to the new pixel divisions and.
Yeah, the star loaders.
Sure. Yep. And for the sky, do you think the sky is stable tonight? How many frames would you recommend? Okay, I saw the nod.
Well, what do you think, Matt? Do you think sky's pretty stable today? I think so.
Extremely stable. Yeah. Yeah.
So yeah, I'm.
So just 3 background exposures then?
If we're moving far away, we probably don't have to debox. Like, if not, like, it doesn't have stars. Okay.
Yeah, yeah.
And how long is the sky exposure? 15 minutes or 5 times 15?
Yeah, so each frame is still 900 seconds.
Oh, just 115. 15 minute, I mean.
50-minute times 3, right? 50.
Do you want 3 frames? I mean, 1 is fine.
Oh, 1 is fine?
Yeah.
Okay, yeah, we can do.
So we'll do 3 in the course of the night, right? In the course of the half night? Did you say we wanted 3, Sherry, at one point?
No, I'm just thinking if sky is not stable, if like we have cirruses, seeing varied a lot, this and that, but tonight it's very clear, sky is very stable.
Okay.
So I think we should spend most of the time integrating on target.
Sure, yeah,
great.
that would be the best.
Yeah, that would be very good.
At the end, we just salute your sky, the patches, and sky, and take a 15, 900.
Yeah.
So near the end, meaning, oh, sorry, go.
So how far away is your sky?
So my sky,
1 degree.
yeah. Let me quickly.
Yeah.
It's mostly a change in RA, not much of a change in deck.
Yeah.
So one of the things we have to do as in an experiment like this is we want to point to a relatively blank patch of sky just to measure what the Earth's atmospheric emission is doing. This is very common in near infrared work, whether you're doing imaging or spectroscopy. That's something we're going to do soon.
Yeah, I think mostly back position around 20 arc minute away.
Okay, so
mostly changing.
I think we move really quickly in elevation.
Or we can, yeah, because earlier I was running the.
Oh, that, okay, oh, gotcha.
But anywhere,
Yeah.
if like the efficient, I think I was choosing
Yeah,
this place.
that would work. That would
And
work.
then RA is about just 1 arc minute away, I think.
1
That-
minute?
Yeah, oh yeah, 1 minute.
1 minute would be about 10 arc minutes, right? Because you multiply by 15 and cosine declination.
Mhm.
So cosine declination will be about, what is cosine of 30? Cosine of 30 is about 0.8 multiplied by 15. Yeah, so about 10 arc minutes
Okay.
in RA and about
RA.
20 in deck.
Yeah, from 39 now to 31 degree. So,
Yeah. Okay.
yeah, it's about 20.
21 arc minutes.
Yeah.
That's not a very big stool. It's less than a degree.
Okay.
Yeah, if it's what 10 arc minute in RA.
Yeah.
That's 1/6 of a degree.
Uh-huh.
We slew 0.6 degrees per second. think this should just maybe a minute or two at least.
Cool. Yeah,
It should be fun. AO setup is really simple because we don't need to guide on anything. So as soon as we move there and hatch is open. And
So there's no AO correction done during the sky?
No
need for it.
Yeah.
We're mostly trying to monitor the brightness of the sky.
Yeah.
And the fixed pattern on the detector, as seen, that's what we're going to try and subtract off.
It's mostly for the OH skylines from your infrared background.
Right. Okay.
And for OSIRIS spectrogram, we have, because these are lenslet arrays, we take the so-called rectification configuration. That's essentially the flat field that you use to take out the response vector. So we have that for you. So you need to take it.
Closure in 15.
Thank you.
15.
And the quick look data cube is using an older rectification matrix
Gotcha.
from previous thermal cycle. So the wavelength calibration is not super precise.
Gotcha.
But we have a new one for this thermal cycle. Or after you reduce data, if you see something weird, I can retake another set.
Gotcha. And Matt said closure in 15, that was 15 seconds.
Yeah, closure, yeah. Oh, actually, closure just happened now.
Just happened.
We're in closure now. That was 15 seconds.
Gotcha. So no laser now.
We have the tiptoe star locked. We're still locked on tiptoe star.
Okay.
So we're not drifting away anywhere.
Yeah, strap still has it. Yeah.
Is it doing any AO correction using natural guide stars or not?
No.
Just tip tilt.
Just tip tilt. Okay, which is still better than nothing.
Yeah. Yeah.
Yes.
Stage 1 AO. Yeah.
Stage 1 AO, right. And it looks like we got through about 600 and little more than 10 minutes of the exposure before 11, maybe not quite 11 minutes, but before the laser shut off.
Yeah. So, and given that the sky is really stable now.
Absolutely.
Yeah.
When we reduce the data, would it be possible to isolate this single 15-minute exposure and compare it to the others? Because I think that'll be quite telling.
You reduce
Because
them frame by frame, then you add them together.
Yeah.
So you can compare, with or without this frame, what the difference is.
right, because I expect that the diffraction limited core of the PSF should be equally good for this exposure as it is for the others, but it'll just have more of a seeing limited component to it, more of the light in a seeing limited component.
Yeah.
Which will be just the Strel ratio will be lower.
Yeah. So you definitely reduce the science frame by frame, or cube by cube that you have together.
Got
and
it.
You can choose how you want to add them together. You might be able to play with the weight.
Exactly. You might be able to give this lower weight. Yeah.
Yeah. I think given that the background is pretty good tonight, stable, by adding this cube, assigning in a way they down.
Here's a radical thought. Should we end the science exposure now and do sky exposures? Since we're not going to do
If
AO.
you end it now, then this exposure time is not quite the same.
It won't be the same, but would that affect the reductions?
I think so.
It
Like you
would,
don't need
okay.
another sky that's
Oh, got you.
ideally identical to your exposure time.
Got it. Okay.
We're almost there.
We are almost there. It's true.
3 minutes.
Not even, right? Not even that. And Sherry, the counter that says 949 seconds, is that because it includes readout time?
Yes.
Okay, so 900 is
We do up the ramp, so it has 64 read.
okay.
So every individual read adds to it. And how many reads it's automatically calculated based on your exposure time. I think there's a lookup table.
So, Raja, in these last 5 minutes that we have for this session, is there anything you can tell us about what you all will be doing for the rest of the evening, or
You know,
Mhm.
if things go exactly according to plan, the rest of the night will be just as boring as the part that you've witnessed. That is, we'll be staying on this star cluster, taking series of 5 times 15-minute exposures. We'll do this occasional step across to a blank patch of sky. We're going to do that right after this exposure ends. We'll take an image of literally a blank patch of sky, nothing in it, just to monitor the spectrum of the night sky and what it's doing. The night sky is very active in the infrared. Is that a laser? Those must be laser. I don't know if you guys could hear the siren.
Yes, that's a laser, and it
Got one more short 5-second closure
Okay.
here.
You mean the laser was back just now?
It wasn't long enough to relaunch it.
Oh, got it. Yeah, so Jamaica will be we'll be sitting on this star cluster the rest of the night tonight, and all of tomorrow's half night as well. The idea is to build up signal to noise ratio to get deeper and deeper. Okay, and the exposure has just ended. Are the stars in the nucleus of M33 large stars in mass and diameter? Somewhat, because the mass of stars, the size and masses of stars, is a function of their age. So if this is a somewhat younger star cluster, then if it was formed a shorter while in the past, then you see
Matt, are we good to propagate again?
you see more massive stars.
I didn't know if we were going to move to the sky position. I thought that's what we were doing. Okay, well, let me get a sky. Let me get a sky. You get a sky. My back.
Yeah.
So right before turnover, we would go to the sky.
Yes.
Is that the plan? Okay.
Yes.
So right before midnight, we'll go there.
Yeah.
We need one for strap too.
Yeah, okay.
Can I apply the offset now, or should I look?
No.
No,
Okay.
not yet. Yeah.
Jamaica, did that answer your question? This when we are on DMOS and we are changing masks and aligning, there's somewhat more excitement. Of course, adaptive optics involves all kinds of behind the scenes excitement that we don't get to see. So the laser was shut off. It's going to be turned back on. We're going to start AO correction again. But Zhuo is refining exactly where in the sky we point before we continue for the rest of the night.
Did it do the background shot for the strap, or?
I don't think the clothes.
I didn't see a move either. I'm tempted to reacquire.
It's a good idea.